So week 9, this is our new topic to talk about. So what we did last week, it was mostly you guys to work on building the Excel file. Are there any troubles with that? Have you learned how to find the response of, that was this topic here. So week 8 was you just needed to go through numerical analysis to determine the displacement response for a single degree of freedom system, which has its own mass and stiffness. And I've asked you to carefully go through the spreadsheets to build all the required formulas to apply both of the Newmark method and the central difference method. So I will assume that's where you are at now, because today basically it's going to be continuation for what we did. We're just going to look at how such results can be used by the designers. So what you done last week is just one step that would need to be applied frequently on different systems in terms of changing its properties, talking more specifically about the natural time period. As we change those properties, we're going to be recording some data, and those data are the maximum response we got from each case. Then from there, we're going to plot what we call it spectra. Yeah, we're going to plot a number of spectra that we use, that the designers or you as a designers can be used to determine the design parameters, for example, the displacement, the acceleration, etc., etc. So let's go through this and we'll talk about it this slowly. Any general question about what we did last week? So I've given you the solutions and you should be able to work out the right formulation until you get your answers same as the ones I've given you. If you did not get the answers, that means there's something wrong with your model, and you can come back to me to work out where went wrong. Okay, now that's what we did last week. So basically, with this introduction, we saying one of the most important applications for dynamics is to determine the response of the structures caused by the ground. So that's basically what we have to do. This week, we're going to be considering that all the vibrations are linear, and that's how we're going to be generating the spectral curves. And we don't assume that there is non-linearity in the building's behavior, which this only will be considered if the building get to the collapse, but we don't want to get the buildings to the collapse stage. We still want to consider, whenever we design a building, we're going to always aim that the building going to be moving under the elastic phase, under the linear phase. We don't want to get it to failure and then start looking what's going to happen to it. That's not what we're trying to do. So the process we will be applying, it will be applied based on the assumption that the system will be working or will be vibrating within a linear elastic system. Right? And that's basically what we're calling it. The analysis we're going to be doing, from which we're going to develop the spectral curves. They will be based on assuming the structures are elastic, where they will be vibrating within that linear behavior of any structure. So looking at this, we have last week start applying the numerical analysis for one ground excitation, right? And what you did so far, you have only considered one time period. Let me open the file just to help me to talk about what we did. You all should have been doing it. I'm just opening the Excel file that I've developed. So what we've done so far, we have assumed there is particular time period, and we've selected it from the example to be 1, right? So this is basically the mass response. That's how the mass is going to respond to that single pulse we looked at last week. There was one single pulse, which is this one. And I did ask you to look at the response. Today, we will use that tool or the calculator we developed to consider a full ground motion, something like El Centro. And it's something like this. So you're going to see here, this is basically the response of that same mass, but today is not for a pulse, it is actually for a ground excitation, as you can see here. Right. So if, as I said to you a couple of times last week, I really want you to be on top of building your tools or calculators so you can smoothly progress with what we're doing this week. Right. So just coming from the same point, it is we will still be using this equation of motion, which we looked at. This is just a repeat for last week. It is just we're going to apply the same equation of motion. But what we have special this week, if we got a real ground excitation, not just a P, not just a force applied on it. And what happened last week? We looked at one property for the structure. It was when the natural time period of the structure was 1 second. But today we will repeat those analyses over different levels of time periods. Now this one here just talks about the how typically those equipments, if we're gonna use a measuring tools, we're gonna be using something like this to measure for us the ground excitation, because last week I did show you these kind of ground excitation, and that was the reason why we started doing it, why we started learning the numerical analysis last week. I said to you, engineers, not scientists who look to the ground motions, not seismologists. I'm talking about engineers who design buildings. They mostly work with these ground motions, right? Now, you see in the news when they got an earthquake, they talk about the Richter value and all these kind of details, but this is not enough for the engineers to work with. Engineers typically need the ground motion records, something like that, to see what's going to happen to the building. The Richter, yeah, gives a very brief idea about the level of damage such ground excitation will impose in a city or an area, but this will not tell you how a particular building can respond to that motion, because the Richter is just the energy that came from the epicenter, etc., etc. Now we're talking about, we are recording the ground excitation. This is just a device which going to measure the response. It's similar to that transmissibility ratio. This device is based on what we studied in week 6 when we talked about harmonic motions, and we talked about one of the devices to trigger motions. So the concept of this device is basically coming from there as well. And this device is going to measure for you such excitation. And where we are starting from in this today's lecture is basically such ground excitation, which is typically recorded with an acceleration. So the horizontal axis is time, and the vertical axis is acceleration. Okay. And in our equations of motions now, these are just basic equations of motions. We will now have a real ground acceleration multiplied by mass to give you the force, which will be equivalent to this total responding force at the mass. So we're still talking about single degree of freedom system, something like this, whether it was vertical system like that, or it was this system. They are both single degree of freedom system. Got a mass, got a damping, and got a stiffness, and the ground excitation is just happening here. or it's just happening there to actually shake your system. So we going through the math, which we're not highly worried about, but in the end of the day, what we're saying to you, to solve such equation under such complicated ground motion, which cannot be formed by an equation, a closed form equation like what we had for the harmonic motions. For example, we can assume it's a sine curve and deal with it. If it was a pulse, we can assume it's a half sine pulse and deal with it. If it's rectangle, we have a way to deal with it. Sorry, if it was rectangle, we have a way to deal with it. If it's triangle, we have a way to deal with it. But now we have a ground excitation. So as discussed last week, we said we're going to be using numerical methods to determine the structural response and any of the methods presented in week 8, which was last week, and I asked you to form that calculator as per the Excel sheet I showed you. Now, so you all have been developing such things, whether for the Newmark method or for the center difference method, and that tool you've developed is able now to tell us how a mass of a structure can respond to a pulse, given that we will define the natural frequency of that single degree of freedom system. So that's where we are at now. Now, we're coming back to the point to understand what's the structural engineering interest, or what's your interest typically. You are interested mostly to determine the displacement of that mass, right? Because that's what we basically design for. And also sometimes we determine the main thing we use in our calculations and checks is the displacement. And also we use the acceleration because it helps us to calculate the force. Displacement will help you to determine whether there is a room for that building to actually vibrate within such amplitudes or not. Now, given that we are assuming and considering all, and you're going to be the engineer who designed your building, going to be within the linear stage, then internal forces can be considered. From the forces from the accelerations can be taken to calculate the bending moments and shear force diagrams or shear actions. Something we kind of applied under harmonic motions. If you remember with the harmonic motions, after we go through the process, we found a relationship between the structural properties and displacement. Then we worked out from the displacement the acceleration or shock coming to the building. Then we worked out for that particular building under particular harmonic motion, we were able to determine the bending actions. We've done those examples a few times before, but that was all under harmonic motion. Now we're going to have real ground excitations. So we're going to work out the displacement. We're going to work out internal forces that will allow us to calculate bending moments and shear forces. And typically that's what we ask you to do as a designer for dynamic actions. So in this week, I will show you how to convert these calculators to one where you will be able to find the spectrum, and then you will use it to determine internal forces or displacements. And then by knowing such parameters, you'll be able to work out the bending moments and shear forces. All right, that's just an example to say the importance of determining where do we use practically the displacement. If you need to assess a building or a heritage building, maybe here we've got a heritage building next to a newly developed building, you have to show to them, to the verifying engineers, or you have to prove to the council that whatever ground excitation going to happen to this building, it will not bond or impact the neighboring properties and get them damaged. So that's kind of, again, it's all coming from determining the displacement level of your newly constructed building. That's if we are designing something new. You still can use the same concept to understand what's going to happen with the existing building. So that's kind of one of the uses for the displacement calculations, which you will see in our examples today. That's what we're finding. And same thing, you all know what we're doing with bending, just to find that the structural element is not overstressed from bending or from shear. All right, so the numerical solution for equation 2, which we stopped at here, yeah, which is, I can tell you in summary, it's same as what we done last week, but we're just going to tweak things a little bit in order to convert it from a pulse to, because last week we had a force, we had the P force coming into the equation. Today we have acceleration, so we just need to treat it with the mass to convert that acceleration to a force and then put it again into the equation, right? And that's basically what we're going to be doing. Maybe it's better to show you this in a real example. So this tab here, for example, which you all did kind of so far up to here, looking to this tab basically is my calculator to determine that single degree of freedom response from a real ground excitation. Here in this course, so this is just basically time, same as what you mostly all did. I'm just listing here a time that will be given to you. That's basically from scientists or the machines, the equipments like this will be used to measure ground excitations. And this ground excitation, I have it plotted here. This is the time. This is the acceleration, meter per second square, right? And what I have here, I've just used a mass figure. So after I multiply the acceleration by mass, it will give me what? A force. So that's what I'm doing here. And then the rest will be same as what we did last week. I'm just using the same equations, the same formulation to calculate the displacement response U of the single degree of freedom system we started looking at last week, right? So you can see here, this was for, again, time period 1. And by the time I change this, let's say 2, the result's going to change. Obviously, whenever I make the building more gentle, I'm making it 5, you can see how the response will be kind of more shaky. You can see here it was 0.15. If I take it back to 1, it will be even less. Now, one of the key things I want you to understand or have a look here is the response should be independent of mass because it will be cancelled out in the equations. So for example, the mass I'm putting here just to form up the equations is 100 kilograms. If I change it to 1,000, the results will not change. So one thing when you're going to do this when you're going to be doing this calculator or updating the one you did last week, make sure the response is not in function of the mass. If you change it, the response will stay same. Now, if you want to understand this, you can divide what I'm saying here. You can divide the equation on M and you will not lose the response because you're able to divide and you are able to actually divide because there is already mass involved inside the C. There is also mass involved in the stiffness. Yeah, we all know that the mass contribute to the stiffness as well, to the overall stiffness. You also know that the mass contributes to damping. Inside the formulation for damping, there's mass. So we are able to divide the entire equation over mass just to take it away, and it will work again. It will give you the same response. You can have a look here. There is no mass here. It's independent of mass. Okay. Now that's what I'm trying to explain to you is the mass is independent, or the displacement response typically is independent of mass. And as you can see here, if we change those values, the calculations here are going to change, but at the end of the day, the response is going to stay same maximum response. That's one thing I wanted you to pay attention to while you develop many calculators like this for making the spectrum. Now, you're going to see later on, while we're here, is once we have a special condition or one condition, well, what I mean with condition is for a specific time period and a specific damping value. So here the damping was 5% and the time period was 1. We will be recording the maximum response. Where is the maximum response here? It is this point. Well, I don't know whether it's actually this point. Yes, it is. It's this point here. Now, how we calculate this point? By finding just a simple function, say maximum minimum of this figure here. Now, if I come here and, or let me go to the displacement, which is this one. I think I put it at the bottom, or maybe some students like to put it at the top. It's up to them. Let me see if I put it. No, I did not. So what you can do, we can use one of the functions to find the maximum response. If I just highlight all this, there is, I don't have here maximum, but I will try to say, I have it. It does not, so that's telling me the maximum was 0.1, but I will also ask him to report the minimum. Have a look here. So the minimum is -0.12 and the maximum is 0.1. So the maximum absolute value is actually 0.12. So what I can suggest you to do and update your calculator with is to plot here the maximum. We can use whatever functions. I leave it to you to research this. There is either absolute maximum. I think I just need to, so there is absolute maximum or minimum. Can anyone suggest something to us? We just need to find, yeah, here we go. So we can use maximum. There are different ways, by the way. I will just say maximum of this. Now I can't say this is only because minimum of same one. Let me put it here. It's G23 to G2217. Close bracket, close bracket. Let's see if my argument is right or not. What I want to do basically, I want to see the maximum, minimum values. But isn't that will give you the, yeah, thanks, Danush, but isn't that will give me, I want the maximum negative or positive. So I think it's not happy with the comma. We just need to read the rules. Because if I do this, it will give me just the 0, 0, and I will be missing the negative. Right? I want it to, I think I have to use another function. Yeah, I want you to think about this as well. I have it done somewhere else, but I just want the students to do it with me. So what I can do here, actually, I can put a comma and say, there's different ways. I will just use one of them. G2217. Close the bracket, close the other one. See what it's gonna do. Have another brackets here and there. Yeah, okay, now it is doing what I want it to do. So this value basically is going to measure for me the maximum response, whether negative or positive we have for that single degree of freedom system when it's excited by this El Centro ground motion. So again, if I go change, for example, the frequency, the time frequency to 5 seconds, yeah, I will have 0.14, and it's almost at the end. So it's here, just this one, this peak. Yeah. If I change the damping to 10%, oh no, this is 100%. So no, 10%, yeah, things will be different. All right, we'll get reduced a bit. Now 0.05. Yeah. So let's see, got some messages there. All right. So do you have questions about what I did here so far? Just get it back to 1, which is the 0.12. So this is basically the displacement of the building, and it is the maximum displacement it would experience within the structure. So what I'm going to do next, you need to copy all this calculator somehow and regenerate, maybe change this to 1.5. You will have now 0.9. Then you need to record the 0.9. So you're going to have another kind of table. Let me just make it here. You're going to have the time period here, and you're going to have the displacement response spectra. And you're going to say for 1 second, we had 0.12. For 1.5, we had 0.09, etc., etc. After you do this for a range of time periods, then this will be called your displacement response spectrum, because you're kind of telling or plotting the spectrum of displacement responses for that particular system or building, whatever it's going to be. Your assessment is going to be the building you practiced. Is there any question about what I did with this calculation here? So what I'm trying to clarify to you, what we did with this equation of motion, we basically same as what you have been practicing last week, but today I'm preparing you to use it for a ground motion, and going to do for ground motion, we have to do a slight change within these columns. Then you will end up applying the same formulas you did last week, which will end up giving you the displacement. But today, because then this won't be the end of what we're doing, because we need to plot the maximum response experience in the structure for different time periods. Remember, here is going to be for the damping will be the 5%. So I will ask you again in different assignments to, let me say here, 2, 2.5, 3, right? So if I change this to 2, now there's going to be 0.18, for example. 6, 2.5, it will be 2, 3, and 3, the last one, it will be 0.2219. So you're going to need to plot this relationship. You also should go back to 0.5 as well. So we can have another, maybe we can have 0 and 0.5. 0 and 0.5. Yeah, here we got very small response, which is 0.044. And basically, yeah, 0 should start from 0. Basically, if you put 0, you got nothing. Yeah. So what I'm doing here, I basically developed a curve. The horizontal axis will be the time period, and the vertical axis will be the displacement response spectra. Right? That's what you're going to be doing in your second assessment for different conditions, for different floors, for different damping. So that was for 5% damping, right? And I will ask you to repeat it, and then I will ask you to provide to me some comments about what you're experiencing. Okay? Any question? Now that's basically a quick summary about how practically you're going to be doing this, but now I'll go back to the lecture notes and show you what I was talking about. So again, as I've discussed, this week we're going to be working with real ground motions, and we're going to be looking at using El Centro, one of the famous ground excitation that happened in 1944 in the States, and well used in different standards and documents, and many high-rise towers and buildings are evaluated for such motion because it can give strong evidence about the buildings' response. Now, someone will ask me, is that what they use locally in the country? Locally, there are synthetic ground excitations. They are less severe than the central. Synthetic came from seismologists. They will end up giving us excitations like this again. They are still like, they look like the ground motions we're working with. So it's something like El Centro, but different amplitudes and different frequencies. They just synthetic, just came from scientists. Okay, so how we are. Again, this is just theoretically telling us how we're doing the response spectral curve. As I've already briefed you, for a particular time period and a particular damping. Here we got 2% damping, 0.6 time period. We're gonna be plotting, and this is for El Centro. So we're plotting the response of El Centro. And let's have a look and see if our tool that we did was accurate. So the damping was 0.02, and what was the time period? 0.5. So this is what we're getting here, which is 0.01, 0.04. Remember, this is in millimeter, but that one was, that was 251. 67 millimeters, that's the response here. So we go at 62 millimeters, and that's what we had at zero damping. Then 0.2. Let's verify it and have a look. As we said, it doesn't matter what we got in the mass, it won't really matter whether you put 100. You will see the calculator is finding another numbers, but when you end up calculating the displacement response, it will stay same, right? So let me have a look. The second is 0.02, and that's 0.5 time period, 0.02 damping. I've got 48. Let me have a look with the new mark method as well. This is my new mark. And let me apply the same. I'm just trying to, I wish from your end, guys, you're doing the same thing. Experience how to use these tools. So what I'm finding for a 2% damping and 0.5 second time period, which is what we got here. Yeah. My calculator is showing me the response gonna be around 50 mil displacement, but this one is 67. So it's kind of different, but maybe they have different properties to work with. So going back to the point is what they're doing here, they actually, in this column here, they the time period is changing from 0.5 to 1 to 2, while the damping is constant. Okay, and in this side, they're actually keeping the time period constant, and they're changing the damping value. So they're just letting you experience. I'm just not sure if this was actually for El Centro or not. That's what I cannot confirm at this stage. But what these plots are telling us here, we can develop a tool, which we had here, that will allow you to either change the damping or change the time period. Then after you develop or be able to develop such plots, you will be able to plot a response spectrum, which is coming to the point I want to take you to. So the response spectrum curve, it is basically, let me have a look here, is this frequency or time period? No, it is time period. So what we're doing here, basically, it is, we're gonna have the horizontal axis as a time period, and the vertical axis will be one of the motions we are dealing with. So it can be displacement or acceleration or velocity. And the other point you need to consider is you have to decide on fixing the damping or changing it, which again, this is something we already prepared in our tool last week, and we have it ready with us. So what this slide is telling us to do is to go and find a maximum. So this process basically is what I did manually by finding the absolute maximum or minimum value here, right? That's the formula I did with you here. It is basically just an implementation for this exercise. So we're telling us if we, after displacement for a given time period and given damping, we have to find the maximum response. Same thing for velocity, same thing for acceleration, right? Then by defining such values for various time period given damping or various damping given time period, you will be able to plot what we call a deformation response spectra, DRS, velocity response spectra, VRS, or acceleration response spectra, ARS. Okay, so the one I took you through here, it is what really we want you to know how to do this week, because you're going to be repeating it multiple times for the second assessment. All right, remember, don't think it's going to be, maybe I should try during the workshop or next week to show you an example, but the sheet will be like this whole calculations should be repeated. You can put it on the side here, because I suggest you to do it automatically, right? Unless you want me to verify it for you. I leave this up to you. How you want to design, we will talk about this during the workshop, how you want to design the final presentation of your spreadsheets, because just to let you know, what you're going to be submitting for the second assessment is an Excel file developed in line with assessment 2, how I put it for you. And there are ways to do this, either to copy these calculations multiple times, maybe 5, 6 times, or you can generate these tables individually. It's up to you. So back to the lectures. So yeah, as discussed before, deformation will be used to answer some questions, and while it can be used to internal, it can be used to calculate internal forces, then it will be very useful to generate a spectrum that will help engineers and designers to quickly find. So someone may ask here and say, why are we doing these spectra curves? Why? Let me show you an example. It's here. This is a spectra curve. By the way, this slide will summarize all what we're talking about. So this is the ground excitation we had from day 1, which is like El Centro. Then we're saying to you, if you got a single degree of freedom system with 0.5 second time period and 2% damping, the maximum response should come roughly at 67 millimeters. If you change the time period to 1, it should come at 0.15. If you change the time period to 2, remember here, we're keeping the damping same. We're fixing the damping. We're changing the time period. So by now, I should be able to plot those 3 points. So I've got here 1 point, 2 point, 3 point. But to come up with all this curve is called the RSD, displacement, DRS, displacement response spectrum. So we need to plot more points, obviously, and that's something we're going to tell you how frequently we want it. So now they just showed you 3 points, how they are plotted. And by the time you got the chance to do more and more points, you will be able to come up with the displacement response spectral curve. And when you develop such curve, it will be very handy for the engineers to use it straight away. So you don't need, engineers don't need to go, like you can say, this chart can be used in Melbourne. Then the engineers don't need to go and do what you have done for 2 weeks. No, they can find the time period of their building and just put it here and work out the displacement anticipated from that building. So basically you are developing, or we're teaching you how to develop a chart that the standards will ask you to use as well. And I will show you, maybe if you looked at the standards you kind of practice for your first assignment. If you go to the section which talks about spectral curves, they will show you what you can use for Melbourne buildings. And what I'm showing you with this topic is how those spectral curves are plotted from real ground excitation. Remember the one from the standard, they are done from synthetic ground excitations, which are simulated for like Melbourne region and regions within the country. Right, but here we just took you through the process of developing your own displacement response spectra, and similarly you can do velocity response spectra, same thing, acceleration response spectrum. So that's really the story behind it. We start from what you developed last week, you repeat it multiple times, then you're gonna work out a spectral curves that you will be asked to use to design a particular structure or building. Okay, so any questions? Now, there's one thing I will share with you as well. The way I showed it to you, how we're doing it here is basically, if you're gonna be double in, like, first thing we have to use numerical method to find displacement, right? So deformation. Now, to find the velocity, you can either double differentiate it, or do it for a third time to find the acceleration. Now, if you're going to be doing this by using refined methods, you can then claim it to be, it is the actual velocity, not the pseudo velocity. Now, pseudo velocity and pseudo acceleration, they are approximate, because there are formulas we introduced you to before, which relates displacement to velocity and displacement to acceleration. Those formulas we talked about a few weeks ago, like 2 weeks ago. If you remember, they were from the harmonic motion topics. We introduced you to formulas which relate the velocity to displacement and also relates acceleration to displacement. If you have used this formula to develop your other spectral curve for velocity and for acceleration, then you should call your charts for velocity pseudo velocity, like approximate velocity and approximate acceleration or pseudo acceleration. However, if you conducted that integration process by using a numerical method, if you have integrated by using the numerical method for a second time and third time, then you would call it the actual velocity spectrum or the actual acceleration spectrum. Okay, so that's basically where those definitions are coming. It depends on whether you have used the formulas or you have used the actual, and these are the formulas I'm talking about. So by all means, we're typically going to be using the numerical calculations to find the displacement spectrum, like what I did here. There is no way to find the displacement by formulas. There's no closed form formula to do that. We have to use numerical analysis and, for example, Newmark method or central difference method that we studied together. So after you develop this, to develop the velocity spectrum curve and acceleration spectrum curve, we can either use mathematical relationship between the velocity and acceleration, or between the velocity and displacement, or between the acceleration and displacement, like what you can see here. You can see here there is a relationship which relates the velocity. This is the velocity component, right? And it can be equal to the displacement. Right, so pseudo velocity is actually the letter D, and if we multiply the displacement response by omega, it would give us the velocity. And you can also, as we all know, the frequency can be replaced by this term, 2 pi over time period. So that's not really something new for you. And as a use for such for velocity, we can actually calculate the strain energy. That sometimes engineers like to know the energy they will have. So from such excitation, if they need to design a damper or something similar to that. But we won't be practicing on using the energy as much as other properties like acceleration or force or displacement. All right, now what I'm basically showing to you here, if you have already generated your displacement response spectrum curve, you should be able to convert it to pseudo velocity curve by applying simply this equation. If you want to make and that's an example of what we did. Right? This is just an example of what we did. So you all understand here we started from a real ground excitation. We have simulated or calculated the response for different range of time periods for a given damping. And then we plotted our displacement spectrum curve. And if you want to convert your displacement spectrum curve to pseudo velocity spectrum curve, you basically can apply this relationship, right? Now, if you need to go further and find your acceleration, pseudo acceleration response curve, you're going to be applying this equation, which comes from double integrating the displacement, or double actually differentiating. This depends on which way we're going. So if you differentiate displacement, you will have velocity. If you differentiate, yeah. So and again, the other use of acceleration, which we all know about, if we have acceleration multiplied by mass, this will give us our force, shear force on the building, and then the shear force can be widely used to determine other stresses on the building. But the key message I wanted to share with you here, if you then want to come up with your acceleration pseudo acceleration response spectrum, you can find out your displacement spectrum curves, the actual one from numerical analysis, then use this relationship to determine your pseudo acceleration response curve. However, there are ways and means where you can use. You remember last week? Let me quickly open it. Someone gonna ask me how we can calculate accurately the velocity or acceleration. I just opened here week 8, and you simply can use what was given to you by the method. Do you remember here? I said to you these 2 steps won't be used last week, but that's where you can use them. And you also need to use that for your assessment when you ask to find the velocity response curve, not pseudo, not the approximate, because we're going to ask you to make all those comparisons and sense them and talk about them in your assessment. So yes, some questions will ask you to plot the pseudo acceleration, and some other questions will ask you to plot the velocity spectrum curves, which are going to be calculated by this relationship by using the central difference method. And the acceleration spectrum curves can be calculated based on this relationship. Remember, you're going to be doing what we did here. So after you find your displacement, you can calculate here your velocity and calculate here your acceleration, and at the top here find the maximum responses. So these tools can be expanded further to do what you have to do, because one of the questions is going to ask you to compare between pseudo acceleration and acceleration, or pseudo velocity and velocity. Let me go back to my week 9 lecture notes, and here I am. So any questions so far about what I've been going through? My notes are closed. So if you're not talking here, can someone explain to me what's this? Can unmute and talk. What was this chart presenting? Or can someone explain to us how we can use this DRS? Yeah, well done. But how are we going to use it? Can you roughly estimate what displacement we can by looking to that scale? And can you roughly tell me if you're building, if you've done the calculations as per the standard, which you did for assignment 1, or from your RCB building, you found that the frequency for your building was 2.5. Can you tell me what displacement you would get there? What dynamic displacement your building is estimated to sway? So your time period is 2.5. What's the deformation roughly? All right, you want a break? All right, so think about it. I just want you to tell me what the displacement gonna be. I think it's all thought of you guys. And in the meantime, just take a break for about 8 minutes. We'll continue at 3:20 from now. Hello again. 340 What do you mean 340 and 2.5? Approximately 250. Okay, the numbers looks promising. So what's this? What's this value here? Based on that, what do you think this value gonna be? 100, isn't it? Yeah, 100 mil. And here it's 200 mil. Yeah, so 2.5. Just hit this and that's it. 250. Approximately 260, 250. Well done, Milan. So 250, that's basically just a simple application for the spectrum curve. But remember what you did with your Excel, you have generated those curves. And you can generate it for velocity, acceleration, pseudo velocity, or pseudo acceleration. Okay. You won't be able to do those Excel sheets if you did not do what we did last week. Isn't it first orange though? No, that's first orange. What do you mean? No, I was asking if you're building that first dot, that point was for a 0.5, was for 0.5 natural time period, which was calculated here. And these calculations helped us to plot this curve. So, but what I was saying, based on such scale, this is roughly 100 millimeters, isn't it? This is roughly 100 millimeters. Yeah, so let me just put them back. I'm just deleting. Oh wait, did it now make better sense? Just delete what I have. So what I'm trying to just let you estimate what this level is about, how many millimeters. And based on the scale we had here, this was about 67. So roughly this would be 100 millimeters. And this is then 200s. This is 300s. And if we take 2.5, it hits the curve here. Then it's roughly 2.6, 260 or 250 millimeters. Does it make sense? Okay. So let's progress. Now, for simplicity, we like to combine DVA all together in one plot, right? We have that triaxial graph that will put this deformation, velocity, acceleration all together in one plot. This is not something possible by Excel. Excel can't do it unless you find a way to do it. That's totally your choice if you like to figure it out. But you can't do this with Excel. There are special softwares to do so. So we won't ask you in assignment 2 to plot such curves. However, they look something like this. Yeah, those plots, they look something like this, where you've got this axis to be the velocity, this axis to be the time period. So always the horizontal axis is time period. The vertical axis here, it is the velocity. This axis here, it is the displacement, D, and this axis here, it is the acceleration. Right? Now, how to use it? Basically, let's assume you have your building with a natural period of 2 seconds. So basically, you're going to put your vertical line, go off the 2 seconds until it hits the curve. See, it did hit the curve here. So you just plot on the chart your 2 seconds until it hits the curve. By the time it hits the curve, you can take it perpendicular on the axis you want to measure the data on. If I want to measure the velocity, just make sure you have a perpendicular angle here, and it will measure 23.5. If you want the displacement, You take it all the way like that until it hits it. It will perpendicular. Remember, we have always the perpendicular angle here. It will give you the 7.47 millimeters, and the units here are in G. Same thing from this point, you go perpendicular to the axis we are interested in, which is acceleration here, and that will give you about 0.191 G. So I'm just explaining how to use it, because I will share with you this kind of generic or general chart. This chart again is from a textbook, and it is for El Centro. And I think I've had a clearer, because here we've got different curves. Each one is for specific damping. That's here. So the lower one is 20% damping. The second one is 10, sorry. The yellow one is 10. Then the blue is 5, 20, 0 damping. Okay, so this is basically a plot which is available in the textbook, and it's plotted for El Centro. So I just want you to know how to use it, because it will be used in some of our examples, or you may be asked to use it in a final exam as well. So make sure you understand how to read it. Make sure you know how to use it and get whatever we need to get out from it. Now, in many textbooks, they may use some different units like inches and pounds, if they are in function of mass. But this is again, this one here is converted to the SI units. So, and again, if you will be asked to use, you're going to be asked to use this chart in the exam. So again, make sure you know how to use it, you know how to apply. I think this one is just an answer for one of the questions we will have in our example, which is coming next. So what we have here is this tower with a mass of 23 kilonewtons, and the height of that tower is 3.7, and the diameter is quite small, so just this very small steel pipes, 100 mil diameter steel pipe supporting the mass. And what else we have? The properties of the pipe. Yeah, they've given you the sectional properties for the pipe. You got the outside diameter of 114 millimeters, inside diameter of 102 millimeters. The thickness of the pipe, it is so something like this. The thickness of the pipe is 6 millimeters. They've given you the second moment of inertia, which you all can work out, but it's all given to you. Elastic, it's about 200,000. And what's this? The weight of the bar, it is this much, 0.1, which I think we can't ignore anyway. The weight of the pipe is 0.16 per meter. So what they want from us, they want you to determine the peak deformation. Yeah, how much it's going to be displaced, and the bending stress in the cantilever due to El Centro. See, and I think with it, when they gave you El Centro, that means they should give you this graph. Right, so that's the question. And they're also saying to consider the damping to be 2%. Okay. So we come here and we start the solution. So I think all these calculations, you should be mastering it if you have already started reviewing your. By any chance, did you have access to your exam dates or not yet? Okay, so the first step here is we calculating the stiffness. And the number was as shown. And the total weight, we're just here putting it, we're just estimating the total weight for the road or for the supporting element, which can be ignored given it is actually distributed along the height of the building. And you can see much more smaller than the concentrated mass. The weight of the tank is 23 kilonewton. The tank, we're just going to convert the mass into kilograms. That's how we can use the units in the formulas. So we've got this much of kilograms. Then the frequency, the natural frequency, maybe you can actually add an n here to call it a natural frequency, will be 3.8 radian per second. And you all know how to work out the time period, which is 1.61 seconds. Now, after you have estimated your time period by visiting or by using this chart, you should be able, so this was the, what was the figure again? That was 1.61. Seconds is up. Double check. Because that seems to be 16 here. Okay. Yeah. So 0.16, you will come here. I think that was for a different example. You don't need to worry about it. Maybe I used it in the second page. No. So can you all double check that if you all agree with this figure? So do you all agree with this figure? Can people check it by looking at the graph? Yeah, so 1.16. You come here. Maybe somewhere here. And what was the damping? What was the damping again? 2%. So the green, which is this one, is our curve. 1.5 is there. I'm going to go up slightly, go to the right. So that's my point here, roughly. And I just go perpendicular to the acceleration. It will give me, actually it's here, yeah, no, should delete it. You just need to be a bit careful. So I'm roughly at this line. So it's approximately there. And then I should be able to work the displacement as well, which is around 120. So let's say what we had here is that Yeah, it says 0.2 G. Yeah, if you want it in meter per second square, you have to multiply it by the 9.81 by the ground gravity. And from slide 21, we do have a relationship between the dynamic displacement and the acceleration. That will give you 0.13. And I think if you want to use the graph, it just gave us the same thing, 120 about roughly. That's what I've seen in the graph. So it's giving us kind of, if you want to use it from the graph, it will give us roughly 120, 130 millimeters. And that's, again, if you want to use the formula that we shared with you, it will give you the same figure here. So by determining the mass and acceleration, our acceleration was 0.2 G. It will work out the force on the mass going to be 4.6 kilonewtons. The bending, you just multiply 4.6 by the height. The bending will be 17, something similar to what you did with your first assessment when you had a high-rise building. Then you just work out your stresses, which I think you all mastered how to do this because you all know what this formula is doing and from where it's coming. So you end up finding your stress at the bottom of the post. And that's it. So again, this shows you a practical application for the spectra or spectrum curve or spectra curves. Okay, so we showed you how the curves are generated and developed from analysis, numeric analysis we started working on last week. And this week, we just took you through the whole process of using it, whether it's someone else prepared it to you or you preparing it, you can use it on different applications. Last week, we were talking about one pulse, but you can say also this week we started advancing the Excel file to work for ground accelerations. And there's another question here, which is talking about a different building. Yeah, I think we do have 3 examples here, which I may ask the students to think with me about. There is no major differences between them apart from some different use for the graph. So this one, we same thing. We do have a frame now, not a cantilever. We do have a frame as shown. The weight of the floor or the slab is given to us. These are things that we have practiced in different topics for harmonic motion, but now we got real ground excitation. So they want you to find the peak response of this frame to the L central ground motion, right? So they give you all the properties you need to know about the frame. Then they want you to find the peak response of the frame. Particularly, they want the peak lateral deformation, yeah, which is going to help you to see where you are at with the deformation at the beam level. And they want you to plot the stress diagram, like something similar to what we did here. Okay, so that's basically what we're doing. And I can see all those basic steps you should be able to top on. Now, just for your information, these kind of formulas will be given to you in a question. We won't let you guess which one to go with. Although we talked about this, in the first week, if you had a pin connection is different than having a rigid connection. Your stiffness is going to be kind of higher if it's fixed like this, but if you have a pin, it's going to be smaller or weaker. This is just the inertia of the section we're having. You've been given all the details for a square post. So the post was a square shape. And here you simply just work out the inertia. Because it's a rectangular shape, we simply used this formula. So at this stage, we should be able to work out the stiffness. And after getting to the stiffness, we should be able to get to the natural time period. Yeah, we should be able to get to the natural time period. Now from here, we just need to get to the damping ratio. That was given to us in the question. And from here, we can go ahead and use the graphs that I showed you how to use. And we found you will be able to find out your displacement response to be 255 millimeters, and your acceleration is 0.1 g. Steps looks easy, maybe because the solutions are here, but students get easily lost between what we studied in week 7 with what we're studying now with what we studied in week 6. Why? I really don't know. Yet sometimes we bring you a question about non-harmonic motions and people solve it as a harmonic motion. That's very, yeah, it's maybe they just didn't study to the end. I really don't know. All right, so things it just needs from you to get trained and learn what you're doing to be on top of it. Right, so there's the next step here. We're simply calculating the forces, and the rest is just same as what we done here. So you just need to end up plotting this, which is just mechanics of solids business, which I leave it to you to practice. All right. Is there any, now this question, I will leave it to you to look at it. The interesting part of this, there's an interesting part with this question. It's your frame got two different heights in terms of their columns, and that will impact the shear value. This is just related to statics, basically. So have a look to the calculation process and see how the stresses will be impacted by such arrangement. So I do suggest you to go through the calculations and compare what's happening with these results and what's happening with the results here, as well as what's happening with the first question we did. All right. Is there any question you want me to go through again, or is there any topic or part or section? So far, what we done last week should be completed on time. If you did not complete it, suggest you to complete it before we meet Wednesday. So this topic is really easy, just helping you to work on your second assessment as well as preparing for the final exam. Definitely questions like the one we're doing here will be something you're going to be working on in the final exam, plus some hands-on practical questions that we can ask you about, just to ensure that you really understand what the numbers are saying and meaning in terms of design. All right, then we should have some decent time to talk about your second assessment as well. That's Wednesday during your workshop. Okay, by getting up to here, I think that will be it for our workshop, for our lecture. I'll still be around if you have any questions about the subject. I'm happy to answer. Stop recording now. you had issues with your Excel sheet or RCB, we do have a room now to talk about it. If you like to talk about it, you can ask me.